So today the first talk will be given by Grégory Faye, which is online, and who will talk about asymptotic behavior of non-local bistable reaction-diffusion equations. You can go, Grégory.
Okay, thank you very much. Thank you for the kind invitation. I'm really so sorry not being in presence today in Montreal, but just from my office in Toulouse. And well, thanks. So as you said, today I want to talk about some work that I've been doing on asymptotic behavior of some non-local bistable reaction diffusion equations. And essentially what I will be trying to do is to present what are the main questions, what have been done. And at the end, you will see that I will be asking you lots of questions because there are still lots of problems that I guess are still open and not really solved at the moment, and very interesting research directions. So let me first start with the basic, or at least the setting that I want to put myself today. So we'll be considering a scalar reaction diffusion equation with bistable type nonlinearity. So here by bistable and throughout the talk, I will be assuming that this is a nonlinearity that roughly looks like the sketch that you have here, but more precisely, it will be a bistable, my nonlinearity. So I will always consider smooth nonlinearities. I'm not trying to get optimal results regarding the regularity. It's not really what matters here. So if there exist essentially three equilibrium points, so two will be normalized to 0 and 1, and there will be an intermediate equilibrium, A, that will be in between 0 and 1. And essentially, if I were only looking at the ODE dynamics, 0 and 1 would be stable, and A would be an unstable equilibrium. And that's also true. So either a question already in the chat or no?
No, it's just
okay.
No question.
Okay, sorry. I've just seen something pop out, and I was wondering if that was for me. And so in terms of stability of the two equilibrium, 0 and 1, I will be assuming that 1 is slightly more favorable than 0. And this is the condition that is below, is that the integral from 0 to 1 of f of u will be positive. And my favorite bistable nonlinearity, and it will be a running example in the forthcoming slides. And it's really illustrative, and you should be thinking about it. It's the simplest one that I can think of. It's just a cubic nonlinearity that vanishes precisely at 0, 1, and A, and that fulfills the requirement with the good properties of the derivative at 0 and 1. Okay, and for such a cubic nonlinearity, the requirement that the integral from 0 to 1 of f is positive, it's simply that A here, the unstable parameter, is between 0 and 1/2. Okay, so the question that I'd like to address today is about the long-time dynamics of such equations when you start from compactly supported initial data. And here I will just be taking a characteristic, I will just have mass on some given interval of length 2L. It's a symmetric initial condition, and essentially 1 and 0. And what I'd like to do is to characterize the long-time dynamics of such an equation. So obviously, unfortunately, for this local equation, everything is well known, and I just want to recap on what are the known results and what you should expect in that case. So essentially, you have two behavior. So say if the mass, so say the interval of your initial condition is very small, then what you get is extension. So uniformly in space, when time goes to infinity, the solution converges to 0. So somehow 0 is stable for this type of initial condition, or you're in the basin of attraction for the steady state 0. On the other end, if the mass is large enough, meaning that the L here, the support of your initial condition, is sufficiently large, then you have persistence of the solution. By persistence, what I mean is that locally uniformly in space, when t goes to plus infinity, you converges to 1, the other stable steady state. And the way you converge to 1 is actually a propagation phenomena, and you propagate at some wave speed that is non-linearly determined by the dynamics. Okay, so these are well-known results, which I think dates back to the 60s and 70s. So 60s by Kernel, that was on the initial nonlinearity, and it's really in Aronson-Weinberger where we get the first results about extension and propagation. And you can find already in this paper 2 thresholds. So L0 would be the threshold to extension, and L1 would be the threshold to propagation. So if you're below L0, then you only see 0 asymptotically uniformly in space. And if you're above the threshold L1, then locally uniformly, you will converge to 1. So these are well-known results, and there are obviously first questions that you can ask. Can you prove, or is it always true that L0 is equal to 1, meaning that there is a sharp threshold, that the transition between extension and propagation only occurs at one given value of your family of initial condition? So this is the first natural question that you may ask. And if you're able to say yes, this is indeed what happens, you may also wonder if you exactly have an initial condition where the support is precisely this value, what can you say about the long-time behavior of the associated solution of the Cauchy problem? So under the setting that I've presented, the answer of the 2 questions have been addressed. So I guess that the very first result dates back to 2005 by Andrei Schlatos. And essentially, he proved the sharp threshold between extension and propagation for this bistable nonlinearity. And actually, there is also for the ignition nonlinearity in his paper, and it has been extended in many directions. So for example, in Du Matano, these are other techniques that are used. So in Pilatos, these are comparison principle techniques. And in Du in Matano, Muratov Zhang, they extended also the class of initial condition where you will also get such sharp threshold. But essentially, the results tells you is that for such bistable nonlinearity, you will get a critical value, L star, such that you either have extension when you're below that value, propagation when you're above. So by propagation, I always mean local uniform convergence to 1. And at the critical value, it's a very nice result, is that you converge uniformly towards a ground state solution associated to the PDE. So by ground state solution, it's a stationary solution. And so this is a profile that satisfies just the ODE with asymptotics where you converge to 0 asymptotically. Because we started from an even initial condition, the profile is also even, and this is why you get this U prime of 0 is 0. And it is monotone on plus and minus, on the 2 half line. Okay.
Hi, Grégory.
Yes. Can
I interrupt? This is Julien. Could you remind me, can you just recall what L is? I think.
Oh, sorry. So L will always be throughout the support of my initial condition. So I have the characteristic function, and minus LL is the support, okay?
Thanks.
And fortunately enough, this should always be the same notation throughout, okay? You will get eventually some L0 and L1, but L0 will always refer to a threshold associated to extension, L1 to a threshold associated to propagation. And when there is a sharp threshold, I will only have one notation, and this will be L star, okay? Where was it? Okay, I was here. So these are very well documented results, and there have been many extensions. So I guess that the key or still ongoing open questions would be, what can you say about this threshold L star when it exists? And can you obtain some quantitative estimates? So for example, how it depends on the nonlinearity, essentially on the nonlinearity. And on the diffusion coefficient, if you add the diffusion coefficient, then the scaling is obvious. But there are still many open questions, essentially of quantitative nature on how can you characterize it more finely. There have been many attempts, essentially formally, either you replace the nonlinearity by something that is piecewise linear so that you can do more computations. There have been some reduction techniques. Anyway, the only thing that I want to mention is that recently, with Mathieu Alfaro and Arnaud Ducrot, we managed to get somehow some better or some indication on how it behaves on the nonlinearity by considering a slightly different class of initial conditions. So you see my initial condition is A. So A is the intermediate unstable state. And I just put myself with A plus epsilon. So in the results by Zlatos, there is also, he also proves the threshold of propagation in that case. Let's denote this Charles threshold L epsilon star, and it's positive. And what we show is that it behaves like log of 1 over epsilon when epsilon goes to 0. There should be a uniform constant here in front of the logarithm, but in our work, we could not get the good one. We just have 2 bounds, and it's actually 1 and 2, and the good constant is in between. So why I'm mentioning this work, it's because later on for what I will be talking about, the non-local case, I will be referring to yet another work by Mathieu, Arnaud, and the PhD student, I guess, of Arnaud, who also obtained similar results, but when you get non-local diffusion. So this is pretty much the picture that I'm aware of in the local case. So there are still many results. And what I want to do today is to ask exactly the same question, but when you change now the mechanism for the diffusion. So here I will be in the situation where instead of the local diffusion that we had before, it will be a non-local diffusion. So D will be some diffusion coefficient. And I've replaced the local diffusion by this operator minus U plus K star U, which is my non-local diffusion. So I will have precise assumptions on K, but just think for the moment that it's integrable, bounded, even, positive. Well, it will have many more properties, but it's a very nice kernel associated, say, to jump to a jump process if you think about a probabilistic interpretation. And once again, the nonlinearity will be of bistable type, and I will still have the same initial condition. Okay. And the question is the same. What can you say about the long-time dynamics, the long-time asymptotic of the solution? So somehow, even though the question is very simple, there are fewer works that have tried to answer this question. And essentially, there are at least one new behavior or one new feature that happens. So essentially, I cannot have, as before, a very nice dichotomy where I would be able to say, independent of, say, D, the connectivity kernel, and the specific form of the nonlinearity, you either fall into 2 behavior, extinction, so convergence uniformly to 0 as time t goes to plus infinity, or propagation. And here by propagation, I always mean this local uniform convergence toward the steady state one. Actually, there is a third asymptotic behavior, which I call stagnation, but sometimes in the literature, it might be called pinning or propagation failure. It depends on from the community where you are. I like the word stagnation because it really reflects the fact that you can start with some initial condition that is compactly supported. And essentially the support of the initial condition does not change. It's not entirely true what I'm saying, but essentially if you start with such an initial condition, it has 2 points of discontinuity. And actually what you get in the stagnation case is that you get a solution that also has 2 points of discontinuity continuity for all time, and the location of this point of discontinuity does not move in time. It remains fixed, it stagnates. And what I'd like to explain today is in which case you get this regime and when you cannot see that regime. So maybe already the take-home message is that this can only happen when the diffusion is small. Maybe you already expected it. Say you take the diffusion is equal to 0, this would be obvious, okay? But it's slightly more involved than this, and it really depends on some properties of the nonlinearity also. It's not always true, okay? And essentially what I want is to explain what type of results we obtain and what we get and what are still the questions that we cannot address yet. But this is really the outline of the talk. So I was mentioning that I had some further assumptions on the connectivity kernel. So for the connectivity kernel, I will normalize it so that its integral is 1. I've already said that it's positive, symmetric. I want it bounded. And for technical reasons that I shall mention later, because I want to use some results later on by Peter Bates and colleagues, I will be assuming that also K prime is in L1 and it has a first moment. And at some time, I will even need a stronger assumption on the localization of the kernel. But these would be, say, the running assumptions that, I mean, you cannot, I think, do better than that at the moment. These are really required. Okay, so that was advertised, I guess, in the abstract of my talk, is that I want to convey some ideas and through some illustration. So what I'm doing here at the moment is I'm fixing a given nonlinearity, I'm fixing a given kernel, and my favorite kernel is this exponential kernel. So I will explain why it's so special. It will be obvious, maybe you already know it, but it will help me a lot to have this specific kernel. The nonlinearity is just the one that I had given. And I'd like to explain a little bit this bifurcation diagram or this cartoon, this figure, before I move on in the talk. So what I've done here, essentially, is I fixed A, so the unstable steady states. And for each value of D, the diffusion coefficient, for that kernel, I'm running extensive numerical simulations. And by extensive numerical simulation, essentially, for each initial condition, so for each L, I'm looking at the long-time dynamics of the solution. So if you're interested in how I'm doing that, I have some very efficient numerical codes that can do that. But anyway, what I'm reporting here is what happens for the long-time asymptotics of the solution. So for a fixed A, for all possible D, and as a function of L, the size of my initial condition, okay? So let's look at first the right-hand side of the figure. So if D is sufficiently large, and it will turn out that for this specific case, sufficiently large will mean D larger than 1/4. And at the end, maybe you will understand why 1/4 will pop out in the analysis. So when D is large enough, essentially what you get, so say, take here and put a straight line, essentially we're back to the sharp threshold results that we had seen in the local case. So here it's just a numerics, but essentially this is what this figure tells you, is that when L increases, I have first extension, and then I have a sharp threshold toward propagation. So this means that if I have an initial condition here, I will have asymptotically propagation. If I have an initial condition here, I have extension, okay? So that makes sense what I'm presenting at the moment. Is it clear? Yes, everyone, no questions so far? Okay, so let's now have a look at when D is really small. So let's say that D is to the left of this pink dashed curve. Here, in everything here, what you get is stagnation. So by stagnation is you get an initial condition here, for example, where there is my mouth, and essentially the long-time dynamics is neither propagation nor extinction. And essentially your initial condition, the discontinuity that you had initially remain pin, and you just converge to a stationary profile, okay? But it's really important that here you're stuck. You do not propagate or you do not go extinct. But once you're in that intermediate regime, so below these two lines, you get several possible scenarios that can happen. So essentially, if I start here for d equal 0.2, and if I cross here, what I get is first I will have extinction for some value of L that are below that blue curve. Then I have an intermediate region where I will get stagnation, and then above the red points and the dark blue curve, I will be back to propagation, okay? So this is what happens, in fact, until this magenta here star, and below this value, I only have stagnation and then propagation, okay? And this is really that figure that I like to comment and explain what we can, how we can, what can be proved rigorously, because here what I've explained, I'm just reporting some extensive numerical simulation, and I'd like to do slightly more than this. So what I will be able to say somehow today is, I will not be able to prove that there is a sharp threshold, but what I will be able to say is that if DL is large enough, I get either propagation or extinction for either small or large L. But I will not be able to get the sharp transition. And what I will be able to prove is that stagnation indeed occur in some region of the parameter space. And I will also be able to characterize what is this dark blue curve and how well it fits with the numerics. But this will be an heuristic explanation. So here I have defined two thresholds. So there is a threshold to extinction, and essentially these are the blue dots here. So this is the largest value for which below you have extinction, and threshold to propagation. And in my figure, these are all the red crosses here, and this is defined like this. So you see when you, so my previous definition of sharp threshold, is when L0 is equal to L1. So this basically happened here, but there is a large portion of parameter space where it's not the case, and there are two different, they take two different values. So obviously, once you can do it for one value of A, you can do it for all possible values of A, and see systematically how it looks like really in full parameter space, because here, once I fix the kernel, I only have three left parameters, which are A, D, the diffusion coefficient, and L, the size of the initial condition. And essentially, you see that the picture remained the same. So obviously, curves are slightly shifting around, but there is always a region where you only have stagnation. There is always a region where you go from stagnation directly to propagation. And this sharp threshold, it always happens at the same value where you get the sharp threshold. Well, and these are all these points that I'd like to explain a little bit and comments. But essentially what I'm saying is that by extensive numerics, you can get these figures, and the idea is, or my aim is to prove as much as possible and explain as much as possible rigorously what happens here. Maybe before I move on, are we just all clear? No questions so far? So I will start with some results in the case when the diffusion is large. And I will start with the simplest regime. It's like extension for large diffusion. So when so assume that we're back in our setting. So F is bistable, K satisfy the running assumptions that I've explained before. So if I define this kappa, which is just the soup of f of u over u on the interval A1, if the diffusion, the coefficient diffusion is larger than K, then I know that there exists some L0, so that below L0 for any solution starting from an initial condition with a support that is below this L0, then I have uniform convergence towards 0. So the proof is really simple. It's just you do your favorite comparison principle argument, and you compare it to a linear system, and that's it for your super solution. Okay, so it's not a difficult one, and it's something that is reminiscent of what has been done before. But what is interesting, or what how can you see it on the previous figure, is that if you specify f to be the cubic nonlinearity, you can precisely determine what is kappa. So it's now some function. So you can check for this value, and what essentially you get is some d that will depend on a. So it's 1 minus a squared over 4. That would be the threshold characterized by d larger than this kappa. Okay, and I will be presenting yet some other figures, but essentially it seems that this condition is sharp within the class of exponentially localized kernel, in the sense that it seems that this is really the good condition that you should be looking at for the onset of extension. So it characterizes precisely L0 star. And I will be explaining and giving more, some numerical evidence for it, but at the moment I cannot really prove it more than what I'm explaining here. So the results is this one. So if now we want to discuss propagation, when the diffusion is large, we are running at least toward one issue, is, or at least the way that I'm seeing it, is like, we see that when we have propagation, so when we converge locally uniformly toward 1, essentially what happens is that the solution propagates, and it's like two counter-propagating fronts that propagate at some given wave speed. So essentially propagation, or this scenario, is conditioned to the existence of traveling fronts for the equation. So essentially what I'm saying is that traveling waves, traveling fronts, which are solution of this equation, and that asymptotically connect the two steady states, one at minus infinity, 0 at plus infinity, and remain between 0 and 1, are really crucial for the dynamics when we are in this propagation regime. So this problem has been extensively studied, and I guess that the first results dates by the work of Peter Bates and co-authors, where they essentially show most of what I will be needing here, so essentially existence, uniqueness, stability, regularity. But what is really important, and the take-home, one of the take-home message of their work, is that you can actually have discontinuous traveling fronts, okay? And discontinuous traveling fronts may exist with 0 wave speed. And they have already devised some sufficient condition for which you can ensure that you will not get discontinuous traveling fronts, because these discontinuous traveling fronts will typically prevent us to have propagation, because they are always associated to 0 wave speed. And so essentially, there is a very nice sufficient condition. It's definitely not a sharp one, but it is sufficient though, is that this map u minus f of u over d, and we'll be showing later that how it's related to other quantities. So if it's strictly monotone on 0, 1, then we know that we have a non-zero wave speed traveling wave. And if we have a non-zero wave speed traveling front, then it has to be smooth, okay? And for the results that I will be presenting, I will further assume that the kernel is exponentially localized. So actually in a recent paper that I was mentioning earlier, Mathieu Alfaro, Arnaud Ducrot, and their postdoc student Kang, they managed to relax this assumption. But essentially, for me, I will need this one, and which gives me the fact that u will be exponentially, will exponentially converge toward the end states, And this slightly simplifies the proof. And this dates back to some results by Coville and Dupain. So essentially the results for large diffusion is as follows, is that if F is bistable, K is exponentially localized with all the assumptions that I had given before. And pending that there exists a non-zero wave speed traveling fronts, I mean a traveling wave associated with a non-zero wave speed. So it has to be positive because of the normalization, but the integral from 0 to 1 of F is positive. Then there is, we can prove that for any L larger than some given value, the solution converges to 1 locally uniformly. And there the idea is rather straightforward, is that you construct appropriate sub-solution that essentially looks like two counter-propagating traveling fronts. And this dates back to what Fife and MacLeod did in their seminal paper. And so what we get here is that the L1 star that I had before is strictly bounded. I mean, it's not plus infinity because in my definition, it could be plus infinity, but in that case, it's some finite number. And if I'm back to the case where I specify the nonlinearity, so if I take the cubic nonlinearity, actually we can derive an explicit sharp condition for the existence of traveling fronts with non-zero wave speed. So this is a work that I did a couple of years ago. And essentially, there exists a formula, a closed formula that relates A, which is given like this. And this tells you that if D is larger than this value that depends on A, then you get zero wave speed traveling fronts for any kernel that are exponentially localized and satisfy these assumptions. Okay. Essentially, what we are at the moment is that if D is larger than the kappa that I had given before, then we have this threshold to extinction. If it's larger than the sup of F prime, which ensures the sufficient condition on the monotonicity of the map G, then we also have this threshold to propagation. And obviously, if D is larger than these two values, then we're back in the situation that we know from the local case, okay? Obviously, many questions that remain open is that in the later case, can we show that there is a sharp threshold? So there is a very recent work by Zhang and Li that show that there is indeed a sharp threshold in the regime of large diffusion. So they have so large diffusion means larger than this condition, and they're working within the class of kernels K that are compactly supported. Okay, and as I was mentioning before, there is this work of Alfaro, Ducrot, and Kang, who also studied quantitative properties of the threshold of propagation for these non-local problems, and also starting from initial conditions that are the intermediate steady state plus some epsilon. And they also derive some asymptotics on the threshold depending on epsilon. So if I come back to what I was explaining before, so if I'm trying to relate what I was showing and the different conditions that we had before. So here, it's on the left is the figure that I have already presented, and on the right is in the parameter space. So for any A and D, what are the regions where you would get sharp threshold or not? And essentially what I'm showing in pink here, it's what I call the pinning boundary. It's below this region here, you get traveling fronts with zero wave speed. Okay, so this is that region. So it's R4 and R5. The extinction region is given by this curve. Okay, and essentially what we get, or what the numeric suggests, and that I cannot yet prove, is that above D equal 1/4, you get a sharp threshold, and in the region where you're in R2 essentially, so above the purple curve and above the pink curve, you don't have a sharp threshold, meaning that L0 is strictly less than L1. So this is essentially what happens here. Okay, so this is what we get, and I'd like to go slightly deeper into the stagnation case in, say, the 5 minutes that I guess I have left. And for that, what is important is yet another class of solutions that are associated to the problem. So I've already mentioned these solutions. So these are the ground states. So these are the stationary solutions associated to the problem. So solution of this equation subject to the fact that asymptotically they go to 0 and they're positive. So they're an existence results that goes back to Kmaj and ran in the late 90s, and essentially it's they're using variational techniques, Palais-Mail techniques, and they prove the existence of solution. And once again, depending on D, the diffusion coefficient, and the nonlinearity, the ground state solution can be discontinuous. And this will be actually the steady state that you select somehow when you're in the stagnation zone that I was mentioning before. The regularity also depends on G, like somehow what we've seen for the traveling fronts. And if G prime is positive, then the ground state is smooth. And in their paper, they also derive some stability with respect to L infinity perturbation for the Cauchy problem, depending on the regularity of these ground state solutions. So if they're continuous, they're unstable, and if they're discontinuous, it's possible that they're asymptotically exponentially stable for the dynamics, and they derive not a sharp condition, but they derive a condition that ensures that. I will not be needing that, but this already indicates that these solutions play a key role in the analysis, and indeed, they do. But one of so the method that they are using is not really constructive, and the strategy that we adopted in our analysis is precisely what I was saying, is that from now on, I will only be focusing on one kernel. So it's very restrictive, but it indicates and gives some flavor of what's happening. So why am I picking this very specific kernel? It's because for the ground state solution, I can totally recast the problem as a dynamical system problem, okay? And this is a trick that is well known and well used, and this allows you to get first results. And essentially, we readily see that, so this is the problem that you have to solve. You have one equation and you get an algebraic equation. And so you can solve for the algebraic equation if you get a monotonicity property for G. And typically, if it's invertible, then you get that the KSRU that I call V will be solution of the second order OD. V minus V prime prime is equal to the inverse by G of V, subject to the same initial, to the same asymptotic condition. And we see that it's highly possible that we cannot do it all the time. There are many cases where G is no longer invertible on 0, 1. And it's possible that it has many, as many as we want intervals of strict monotonicity. And essentially what I will be doing from now on, I will be assuming, and it's just what happened for the cubic nonlinearity, I will be assuming that it has only 3 intervals of strict monotonicity. So it's essentially the assumptions that I'm making here, but illustrated by this cartoon that the function G of U is not strictly monotone, but it has 3 intervals of strict monotonicity. So in that case, what you do in order to solve for your problem for ground states is that you will be able to invert the function G on its both interval of monotonicity. So you will be able to invert it here from 0 to beta, and you will be able to invert here from gamma to 1. And it's essentially what you do. And you're led to study 2 dynamical systems, and to get solution, you will intersect and glue together phase portrait. And it's what I'm trying to illustrate here In blue, this would be the trajectory that you get from one part of the problem. And in dark red, this is the trajectory emerging from the other part of the problem. So here, because I'm gluing things together in the variable v, I'm constructing a ground state that is continuous, but obviously when I'm getting back to the original variable u, I get discontinuous ground states with here precise location of the point of discontinuity. And what I'm doing, I'm expecting ground state with only two points of discontinuity in that setting where the map G is monotone on a maximum of 3 intervals. So it's typically what you get. And obviously, depending on the form of the nonlinearity, you have many possible scenarios for the phase portrait and how you glue them all together. You can even get ground states that are regular, obviously continuous. And so essentially everything is summarized in this cartoon is that you can determine, typically fully determine for the cubic nonlinearity what you get. And typically you get region where you get only a smooth profile, you get region where you get a 1 parameter family of discontinuous ground states, you get region where you get a smooth profile and a 1 parameter family of discontinuous ground states. And you can precisely characterize rigorously, I mean, all these boundaries in the case of the cubic nonlinearity, these are exact formula that you can derive. And here I've presented the pinning region. But now that we get the existence of ground states, you can construct appropriate sub and super solution to the initial problem to show that you will prevent solution to go extant or prevent solution to propagate. And it's essentially the two results that I'm mentioning is that you can, for this specific kernel and a nonlinearity so that G is monotone on a maximum of 3 intervals, then you can get condition for which you get a non-extinction result. And similarly, you get a different set of conditions for which you get non-propagation. So essentially, the solution is blocked by a ground state solution that will not propagate. And as I said, the idea is to use this ground state solution and construct appropriate sub and super solution. And you can find a non-empty region in the parameter space where you can combine these both results and you get what I would call a light or an intermediate stagnation results, meaning that the solution will be blocked by below and by above by this ground state solution, and so will remain pinned and will neither go extant, nor it will propagate. And obviously what the numerics, all my numerics suggest is that we should have here on the left and on the right exactly the one unique ground state, and the discontinuity of the ground state associated should be precisely the discontinuity that we gave with the initial condition. So it should be at plus and minus L, but we're not yet there. And well, we can put everything back together. And I guess it's time for me to conclude. And this is my last slide, is that I've tried to explain and essentially convey a message that for this nonlocal diffusion bistable equation, when the diffusion coefficient is small and for some particular values for the nonlinearity, you can get a different behavior, asymptotic behavior that I call stagnation. And when you pick a specific kernel and you specify also to a specific nonlinearity, you can get more information and try to get some sharp boundaries of what's happened or not. And I had said that I would explain what is the blue curve. So it's just a formula. So this is the maximum of the discontinuity points associated to the family of ground state solution. So it occurs precisely at A being the unstable intermediate steady states. And this is exactly, I mean, this seems, it's just a conjecture that the L1 star is precisely given by that value, and it's always the case. And I will just stop here. And thank you for your attention. And I'm sorry that I was a little bit late.
Thank you, Grégory. So who has a question.
Yeah, hi, Grégory. Thank you so much for a really nice talk. So I was wondering whether you can reproduce at least some of the phenomena with nonlinearities of FKPP type. So what I have in mind is the following. So say you again take a nonlinearity which vanishes at 0 and a, just to stick to your notation, and is negative in between, but then is say concave. So for example, take the parabola which is 0 in which has zeros 0 and a, and is negative in between, and then goes to infinity outside of it.
Yes. Okay.
Right, and then. I mean, so my intuition is that kind of the stable point 1 should not really matter. So if you take an initial condition, which is then again 0 outside some compact interval and a little bit above a inside this interval, do you have the same phenomena?
So, okay, so I think that I understand your question, and I will try to rephrase it with my own terminology. So what you're saying is that is what you describe robust if so let's know, I think that was fine. If here in front of the initial condition, instead of taking 1 as a saturation, I take any value between a and 1. Is it your question?
Well,
if it was your question,
you do. So okay. So I was thinking of that when I saw your result that you where you take an initial condition which has a factor a plus epsilon in front.
Okay, but so that's perfect. So, but
maybe it also works for this one. I don't know.
No. It's my point. It's like if you put an alpha here in front of the initial condition, and this alpha is between a and 1. You essentially what you're doing in this cartoon is that you're adding a third direction. I mean, you should be having the same kind of picture, but now there is a third direction with alpha. And essentially what I'm saying is that stagnation would also occur, and you would also get similar behavior when you vary alpha. This is something that I've done, but I'm not presenting here. But there are also, yeah, I'm not so sure if I really answered well your question, but you would recover similar behavior as what I've presented, but eventually maybe stagnation will disappear if alpha will get close to A. There are some, I would call it bifurcation, but there are some other behavior that happened there. And essentially in what Mathieu Alfaro, Arnaud Ducrot, and their students, what they did, they also studied the same problem with A plus epsilon, but they always stick in the region where D is sufficiently large so that they're essentially in a propagation / extinction regime, and they don't see the stagnation part. So they always require, we assume that we're in that regime.
And so just to come back to my original question, so do you then think that, so if I replace the nonlinearity by a parabola, which goes to infinity to the right and to the left and vanishes at 0 and A, do you think that you can again get a stagnation regime here? If that was the case, then this equation would have a really, really nice interpretation in terms of branching rounding motion.
Okay, so of course, I've never thought about it before, and I'm pretty sure that if I say something, it will be stupid. I would have to think about it and give you the answer when you're back in Toulouse. But
okay.
I don't know. I mean, what would really matter, it's in terms of stagnation, is how I see things. It's really intimately related to this ground state solution, or the fronts that are blocked. Okay, so I would first try to translate if I could construct discontinuous ground states, because if I get one parameter family of ground state solution, it's really likely that they will be stable and that I will be able to prove that there is still stagnation. So my I mean, the first direction that I will be looking is just trying if I can get these, say, ground state solution that are discontinuous. Still, in the way that I'm constructing it, I'm really using more. I mean, I'm really using the fact that one is an equilibrium point as much as 0 is in the construction of ground states.
So
Thanks.
Can I just make a quick comment? So I think that the answer to your question is you could maybe construct ground states that are very particular, but they're not going to be as stable, so you won't have the same stagnation. So my understanding of the stagnation result, Gregory can tell me if I'm totally wrong, is that when D is 0, basically anything that's 1 stays 1, anything that's 0 stays 0. And so you can have this kind of, you have stagnation of anything that starts, you know, as an indicator function. And then when D is small, you're basically just saying that you're not so far away from this phenomenon. But if you change the nonlinearity to what Pascal's suggesting, basically what you could have is if you just start with a kind of initial data that is near 1, it's just going to grow and grow and grow and grow and grow. Eventually it's so huge that the tails of the diffusion nonlocal operator will be able to like shove it out and start propagating. But that would be my guess. But
yeah, I think that I agree. But really here it's like this stagnation or pinning region or whatever you call it. It's really not D equals 0. I mean, it happens really for D large somehow. I mean, D is 0.2, but it's not really something that you only get when D is go to 0. So I don't know. I mean, I would have to think about it.
Maybe one last quick question.
Okay. So yeah, maybe Sarah should be asking this question actually, but I was wondering if you know, this seems to be ripe for using the voter model interpretation of Sarah and Alison. And I was wondering if you had thought about that, particularly in terms of stagnation. D small correspond to having, so if you keep diffusivity fixed, this correspond to having large branching rate, right?
So definitely not.
Okay.
I've definitely not thought about it. But yeah, it's something that I mean, having a different interpretation and a different point of view would definitely help a lot. I mean, getting beyond, say, the exponential kernel or having a different idea, because, you know, I've tried, because I like numerics, so I've tried to reproduce these results and see, say, okay, take a Gaussian kernel that have similar properties, or at least their Fourier transform at low frequencies, they have the same coefficients. And I can see that qualitatively I obtain, I mean, that's what I'm showing at the moment. It's like I obtain similar behavior, but obviously the curves are not, they're not the same as expected. But say for the Gaussian, I cannot say anything at all. It's so specific to what I was able to do and to get lots of information on the ground state by using this dynamical system point of view. So yeah, definitely interested and looking for a different formalism to look at this problem.
Okay, I guess we can thank Grégory again for this nice